This is our financial maths revision video. Throughout the video, we're going to look at, first of all, equivalent interest rates. So we're going to be looking at maybe converting from a yearly rate to a weekly rate or a monthly rate. That's going to lead us on then to looking at a little bit of revision on our geometric series as part of our patterns, because that will help us then with finding the installments as part of our savings, or our annuities, basically, our regular installments. And then finally, we're going to look at pensions. So we're looking basically at interest rates, savings and pensions throughout this video. Here's a typical exam question. Marion contributed €100 at the end of each week for 20 years to a pension fund earning 4.6% AER. Find the rate of interest per week which would, if paid and compounded weekly, be equivalent to an effective annual rate of 4.6%. So very text heavy really here, but basically what it's getting us to do there in part A is they've given us a yearly rate, which is 4.6%. They want us to find what's its equivalent interest rate per week. So in order to do this, we need to have a little bit of knowledge of our compound interest formula. So F is equal to P bracket 1 plus I to the power of T. Now, I only need the 1 plus I to the power of T part of it, because the amount of money is irrelevant when I'm looking at the interest rates. And I'm going to look at it for two parts. I'm going to look at it for the year, and I'm going to convert it or compare it to the weekly. So I'm basically doing it out twice. So 1 plus I to the power of T. And they're going to equal each other. Now, I need to know what the interest rate for the year is. It's 4.6%. Well, let's turn that into a decimal by dividing it by 100. So that's 0.046. So in my yearly rate, it's going to be 1 plus 0.046. So that's giving me 1.046 to the power of T, which is 1 year. And that's equal then to 1 plus I. That's the interest rate that I need to find. I don't know that yet. And I do know my power. It's going to be 52 weeks. So to the power of 52. Now on the yearly side here on the left, 1.046 to the power of 1 just remains as 1.046 equals 1 plus I to the power of 52. Now that power of 52 is going to be a problem. So I want to get rid of it. How do we get rid of it? So to get rid of that power, we can either find the 52nd root, or you could multiply both sides by 1 over 52, the power of 1 over 52. Because if you multiply 52 by 1 over 52, you'll get 1. And like everything in equations, if you do it to the right hand side, you need to do it to the left. So over here on the left, I'm going to put it to the power of 1 over 52. So on our yearly side, 1.046 to the power of 1 over 52 is leaving me with 1.00086,525 is equal to 52 times 1 over 52 gives me 1 plus I to the power of 1. 1 plus I to the power of 1 is just 1 plus I is equal to 1.00086,525. I'm going to subtract 1 from both sides, or moving over that 1, which is going to leave me with I is equal to 0.00086,525. And to turn that into a percentage, I'm going to times it by 100. So that is leaving me with a percentage rate of 0.086,525. So that's my weekly equivalent rate to 4.6%. Okay, I'm now looking at part B. How much was her lump sum payment to the nearest euro when she retired? So I'm going to look at this first of all as a number line. So let's see what happens basically over this 20 years. So Marion is starting off now. So I'm just going to call this day 1. So now, basically. And she's finishing her installments in 20 years' time. Well, 20 years' time is how many weeks? So 20 times 52, 1,040. Okay, so just imagine in another week's time. So in 1 week time, 2 weeks time, and so on and so on and so on. So we're up here to 1,039 weeks time and 1,038 weeks time. So we've all these 1,040 weeks between now and 20 years time. So what do we know? Marion contributes €100 at the end of each week. So her first €100 is basically going in here. So that's when she's lodging her first €100. So there's nothing happening basically from now. I only opened the account, or Marion opened the account today, but for that first week, nothing happens. She puts the first €100 in at the end of the first week. So we need to look at how long is that €100 in the bank for? Well, that €100 is not in the bank for 1,040 weeks. It's only in there for 1,039 weeks, because that first period we're leaving out, that first week, because it says at the question that it's going in at the end of each week. So we're now going to look at what happens with that €100. Well, that €100 is going to have to earn interest. So the interest rate we found from part A was 0.086525. So that €100 is going to be multiplied by 1.000865525. And I'm going to put that not to the power of 1040, but to the power of 1039. It's in there for 1039 weeks. Look at our last €100, or Marion's last €100. It goes in at the end of the week, so it's basically going in on the 1040th week. Now, it won't earn interest, because think of it like this: it's going in today, but it's also coming out today. So that €100 isn't earning any interest. We can just leave it as €100, or we could write it as 100 bracket 1.000865525 to the power of 0. It's the same thing. So what does that look like now as part of our geometric series? So we want her lump sum, what she wants to earn, or how much she wants to save basically. And I have all these regular installments. My first one, €100, 525 to the power of 1039. My next one, in 2 weeks' time, will only be in the bank for 1038 weeks. And so on and so on and so on until my last couple of installments. So my second last installment will earn interest for 1 period, and then my final €100, as I said, which goes in on week 1040, earns no interest. That is also the same as putting it in ascending order. So start with the €100, go then to 100 times 1.0008625 to the power of 1, and so on and so on and so on until I get to my last 1.000865525 to the power of 1039. I've just reordered it. I'm starting with the lowest value, basically, the €100. That makes life a lot easier when I'm going to insert it now into my sum of all terms formula. So you can see here now that I have a sequence. Well, I actually have a series because I'm adding them together, and I have a geometric series because it's going up by a power. And if I go to my log tables, the formula for the sum of all terms in a geometric series, the sum, Sn, is equal to A times 1 minus r to the power of n all over 1 minus r. That's the formula that's in my log tables. Now, if I just write down some pieces of information here that I know of, what do we know? Well, we know that the n is 1040. That's the amount of weeks in the 20 years. My first term is A, which is €100. And my R is the ratio. What's it increasing by each month? Well, it's increasing by the power. So my R is 1.0008625. That's what it's going up by each week. And I'm just going to put them into my formula now and evaluate that on the calculator. So Sn, or S1040, that's the amount of weeks. A is my 100, multiplied by 1 minus 1.0008625 to the power of 1040, all over 1 minus r, 1.0008625. Working that out is €168,540. I'm actually, just for simple terms here for the example, I'm going to leave out my decimal. So roughly €168,540 in Marion's pension pot, or in her savings account basically, in part B. C is very similar to part A. find the rate of interest per month, which would, if paid and compounded monthly, be equivalent to an effective annual rate of 3.8%. So part A looked at a weekly equivalent rate, now we're looking at a monthly rate. But I'm going to do it the same way. So we have our year and we'll have our month. My year, again, once again, I'm taking my 1 plus I to the power of t, coming from my compound interest formula. Again, I don't need the amount. You can put a 1 there as your p if you want. My interest rate for the year is 3.8%. Divide that by 100 to get it as a decimal, 0.038. So that will give me 1.038 to the power of 1, 1 being my time for 1 year, is equal to my monthly rate, 1.I to the power of t, which is 12 for months. Okay, so 1.038 to the power of 1 remains as 1.038. In order to get rid of the 12 to make it 1, I get the 12th root or multiply to the power of 1 over 12. And if I do it to the left, or sorry, to the right, I must also do it to the left. So that is giving me 1.00311128 equals 1 plus I to the power of 1. And that is 1 plus I is equal to 1.00311128. Subtracting 1 now from both sides is giving me 0.00311128 is equal to I, and we times that by 100 to turn it into a percentage. So that is 0.31128%. That's my interest rate per month. And that's part C. Looking at our final part now, D. So in part D, we need to think of Marion as though she's now retired. So she's done her savings in part A and B for 20 years, and she's now happy out in her retirement. And Marion is using her lump sum that she saved in B to buy an annuity at 3.8% AER, giving her an allowance at the end of each month for the next 20 years. How much is her monthly allowance to the nearest euro? Now, we have a lot of information from up above here. The interest rate of 3.8%, we have found that out already up above, so that's the annual rate. We've converted that now to a monthly rate up in part C as 0.31128%. So that's one thing that we do know. We also know from part B, so that was from part C, we know from part B that her lump sum is 168,540 euro. That's what her lump sum that she saved is worth. And she now wants to divvy out that lump sum over the next 20 years of her retirement. So pensions are a little bit different to savings, because with the pensions, what you're trying to do is get the present value of each of the payments that this person, Marion, is going to receive at some future date in time. So we're still going to be looking at our compound interest formula, which is F is equal to P times 1 plus I to the power of T. Now in part B to this question, when we were looking at savings, we only looked at this part, the present value of that installment into the savings account. But what we're now trying to focus in on is the future value of that amount of money. So what I'm now going to do is basically divide across by the 1 plus I to the power of T to get P on its own. So I'm dividing across by 1 plus I to the power of T. And it's this part now that we're going to use as part of our pensions, because as I said, that's going to get us the present value of some future payment. So when I set up my geometric series, that's what I need. F over 1 plus I to the power of T. Now, like my savings, I'm going to do a number line here to see what's happening with Marion's lump sum. So she's starting off today. We'll just call it, this is 0 time. And this is her full money of 168,540 euro. That's what she's starting off at. And she wants some payment after each month. So that's our first month. She'll have some payment coming in the second month, and so on and so on. And it's 20 years again, and it's monthly. So 20 times 12 this time is giving her how many installments? 240 installments. So up to month 240. Okay, next thing we need to evaluate is when are these installments coming? So the question says that it's giving her an allowance at the end of each month. So her first installment is coming at the end of month 1, and we need to find out the value of that installment. We are not receiving an installment at the first, which is right now, so we're not getting anything there. And she will get an installment each month. So in the second month, in the third month, in the fourth month, in the 239th month, that should read, and the 240th month. So she's getting all those installments. We basically want to find out what is that installment worth. Now, we can also see here that these installments are going to earn interest because we're lodging that money into the bank account, and they will earn interest as it sits in the account. So I'm putting f over 1 plus I to the power of t. Now that last installment, let's have a look at that and see, is it actually earning interest? Well, we can hopefully see that it is, because this money has been sitting in the bank account for 240 months, so it is earning interest, and it's going to earn interest for 240 months. So it's going to be 1.0031128 to the power of 240 months. Coming back to the start though, my first installment is coming out after 1 month, so it will also earn interest at 1.0031128, but it will only earn interest for 1 month because it's only going to sit into the bank account for 1 month until Marion receives it as part of her pension installment. So I'm going to set up my geometric series now based on that information. So we're going to have our lump sum of 168,540 euro equals f over 1.0031128 to the power of 1 plus f over 1.0031128 to the power of 2, and so on and so on and so on and so on, up until f over 1.0031128 to the power of 240. I now notice that I have a series. I have a geometric series because it's going up by a power. So once again, I can use my sum of all terms formula for my log tables. A times 1 minus r to the power of n over 1 minus r. Filling in pieces of information that I know. A is my first term, which is f over 1.0031128. My r is the ratio that it's going up by. And think about this, it's going up. Well, how is the f going up? Well, all I'm doing there is timesing by 1. So it's a fraction this time, so it's 1 over. And on the bottom, the denominator, it's going up by my power. So it's going up by 1 over 1.0031128. So that's my r. My n is the number of installments, which is 240. So let's fill that into my formula now. So Sn, which is my lump sum, 168,000 euro, 540, is equal to A, which is f over 1.0031128 times 1 minus r, which is 1 over 1.0031128 to the power of n, which is 240. So it's actually advanced algebra here, basically. That's what this question is getting us to do. 1 minus r, which is 1 over 1.0031128. So I'm going to take it in stages here. So on the denominator, so I have 168,540 is equal to f over 1.0031128. And on the denominator, as I said, 1 minus 1 over 1.003 is giving me as a decimal 0.003103. On the top here, inside the bracket, let's see what that gives me. 0.525698. What I'm now going to do is I'm going to put the 168,540 over 1 and cross multiply. So that is leaving me with 1 multiplied by the f over 1.00. So that's giving me f over 1.00311128 times 0.525698 equals 168,540 by 0.003, 522.98. Next thing I'm going to do, I'm going to sort out this left-hand side. I'm going to put the bracket over 1. I have two fractions, multiplying fractions, top by top, bottom by bottom, is leaving me with 0.525698f over 1.00311128 is equal to 522.98. Put that over 1 and cross multiply again, which is giving me 1 multiplied by 0.5 is 0.525698f is equal to 1.003 multiplied by 522. 524.61. Nearly there. Now I want f on its own. To get f on its own, I'm dividing both sides by 0.525698. So that is giving me an installment of €997 and about 93 cents. So about 998 euro. And that's the end of our financial maths question.